Hi! Sa mga nakaraang discussions, we've already knew what is the meaning of floods. According to that, a flood is an unusual high stage in a river, normally the level at which the river overflows its banks and inundates the adjoining area. Ngayon naman, pag-aaralan natin ang tatlo sa mga subtopics nito. Ito ay ang flood frequency study, ang Gumbel's method, at ang Log-Pearson type 3 distribution. Let's start up with the first subtopic under floods, which is the flood frequency study. Ano nga ba ang flood frequency study? Flood frequency analysis or study is a technique used by hydrologists to predict flow values corresponding to specific return periods or probabilities along a river. The application of statistical frequency curves to floods was first introduced by Gumbel. Hydrologic processes such as floods are exceedingly complex natural events. They are resultants of a number of component parameters and are therefore very difficult to model analytically. Another approach to the prediction of flood flows and also applicable to other hydrologic processes such as rainfall is the statistical method of frequency analysis. The values of the annual maximum flood from a given catchment area for a large number of successive years constitute a hydrologic data series called the annual series. The data are then arranged in decreasing order of magnitude, and the probability P of each event being equal to or exceeded is calculated by the plotting position formula, which is P is equal to M over M plus 1. Where M is the order number of the event and N is the total number of events in the data. The recurrence interval T, also called the return period or frequency, is calculated as T is equal to 1 over P. The relationship between T and the probability of occurrence of various events. Thus, for example, the probability of occurrence of the event R times in n successive years is given by P sub Rn is equal to the combination formula P raised to R Q raised to n minus R, which is equal to n factorial over the quantity of n minus R factorial P raised to R Q raised to n minus R, where Q is equal to 1 minus P. Chow in 1951 has shown that most frequency distribution functions applicable in hydrologic studies can be expressed by the following equation known as the general equation of hydrologic frequency analysis. It is the x sub d is equal to x bar plus k lowercase sigma. Kung saan ang x sub t is the value of variate x of a random hydrologic series with a return period t, ang x bar naman is the mean of the variate, the lowercase sigma is the standard deviation of the variate, and k is the frequency factor which depends upon the return period, t, and the assumed frequency distribution. Some of the commonly used frequency distribution functions for the prediction of extreme flood values are: number 1 is the Gumbell's extreme value distribution, the second one is the Log-Pearson type 3 distribution, and lastly, the log-normal distribution. Let us now proceed with the second subtopic under floods, which is the Gumbell's method. The Gumbel method of frequency analysis is based on extreme value distribution and uses frequency factors developed for theoretical distribution. The method utilizes general equation given for hydrologic frequency analysis. Delta x is departure of variate from the mean. This extreme value distribution was introduced by Gumbel at 1941 and is commonly known as Gumbel's distribution. It is one of the most widely used probability distribution functions for extreme values in hydrologic and meteorologic studies and prediction of flood peaks, maximum rainfalls, maximum wind speeds, and many more. Gumbel defined a flood as the largest of the 365 daily flows, and the annual series of flood flows constitute a series of the largest values of flows. According to his theory of extreme events, the probability of occurrence of an event equal to or larger than a value x sub 0 is P to the quantity of x greater than or equal to x sub 0 is equal to 1 minus e raised to negative e raised to negative y, in which y is a dimensionless variable given by y is equal to alpha to the quantity of x minus a. Alpha is equal to x bar minus 0.45005 x sub 0, and alpha is equal to 1.2825 over lowercase sigma sub x. Thus, y is equal to 1.285 to the quantity of 1 minus x bar over lowercase sigma sub x plus 0.577, where x bar is the mean and the lowercase sigma sub x is the standard deviation of the variate x. In practice, it is the value of x for a given p that is required and is transposed as y sub p is equal to negative ln to the quantity of negative ln times the quantity of 1 minus p. Noting that the return period t is equal to 1 over p and designating y sub t is equal to the value of y, commonly called the reduced variate for a given t, y sub t is equal to negative to the quantity of ln of t over t minus 1. Y sub t is then now equal to negative quantity of 0.834 plus 2.303 log of t over t minus 1. Now, rearranging equation y is equal to 1.285 times the quantity of 1 minus x bar over the lowercase sigma sub x plus 0.577, the value of the variate x with a return period t is x sub t is equal to x bar plus k lowercase sigma times x, where k is equal to the quantity of y sub t minus 0.577 over 1.2825. Under Gumbel's method, meron naman tayong tinatawag na Gumbel equation for practical use. Equation x sub t is equal to x bar plus k lowercase sigma sub x, giving the value of the variate x with an recurrence interval t is used as x sub t is equal to x bar plus k lowercase sigma sub n minus 1, where lowercase sigma sub n minus 1 is equal to the standard deviation of the sample size n, which equals to the square root of the summation of the quantity of x minus x bar squared over n minus 1, and the k is equal to the frequency factor expressed as k is equal to y sub t minus y bar sub n over s sub n, in which y sub t is equal to the reduced variate, a function of t, and is given by y sub t is equal to negative ln times ln t over t minus 1. Y sub t is equal to the negative 0.834 plus 2.303 log t over t minus 1. Y bar is equal to the reduced mean, a function of sample size n, and the s sub n is the reduced standard deviation, a function of sample size n. These equations are used under the following procedure to estimate the flood magnitude corresponding to a given return based on an annual flood series. Number 1. Assemble the discharge data and know the sample size n. The annual value is the variate x. Find x bar and lowercase sigma sub n minus 1 for the given data. Second, determine yn and sn appropriate to the given n. Third, find yt for a given t. And fourth, find k. And the last is determine the required x sub t. Under the Gumbel's method, we also have the Gumbel probability paper. The Gumbel probability paper is an aid for convenient graphical representation of Gumbel's distribution. It consists of an abscissa specially marked for various convenient values of the return period t. We also have the confidence limit. The confidence interval indicates the limits about the calculated value between which the true value can be said to lie with a specific probability based on sampling errors only. For a confidence probability C, the confidence interval for the variate x sub t is bounded by values x sub 1 and x sub 2 given by x sub 1/2 is equal to x sub t plus or minus f to the quantity of c, S sub E, where FFC is a function of the confidence probability C determined by using the table of normal variate as C in percent and the FFC. In 50, we have the 0.674. In 68%, we have 1. In 80, we have 1.282. In 90%, we have 1.645. In 95%, we have 1.96. And 99, we have 2.58. In the previous equation, we have seen the SME. It is equal to the probable error, which is equal to B times lowercase sigma sub n minus 1 over the square root of n, where B is equal to the square root of 1 plus 1.3k plus 1.1k squared, and k is the frequency factor, and the lowercase sigma sub n minus 1 is the standard deviation of the sample, and n is the sample size. It is seen that for a given sample nt, 80% confidence limits are twice as large as the 50% limits, and 95% limits are thrice as large as 50% limits. Let us now proceed with the third subtopic under flood, which is the Log-Pearson type 3 distribution. The Log-Pearson type 3 distribution is a statistical technique for fitting frequency distribution data to predict the design flood for a river at some site. Once the statistical information is calculated for the river site, a frequency distribution can be constructed. In this, the variate is first transformed into logarithmic form or base 10, and the transformed data is then analyzed. If x is the variate of a random hydrologic series, then the series of say variates, where say is equal to log x. For this say series, for any recurrence interval t, gives say sub t is equal to say bar plus k sub say times the lowercase sigma sub say, where k is a frequency factor which is a function of recurrence interval t and the coefficient of skew c sub s. Alpha sub say is the standard deviation of the say variate sample, which is equal to the square root of the summation of the quantity of say minus say bar squared over the n minus 1. C sub s is equal to the coefficient of skew of variate say, where it is equal to n times the summation of say minus say bar raised to 3 over n minus 1 times n minus 2 times lowercase sigma sub say raised to 3. Say bar is equal to the mean of say values, n is equal to the sample size, which is equal to the number of years of record. The variations of k sub say is equal to f to the quantity of say sub s and t. After finding say sub t, the corresponding value of x sub t is obtained as x sub t anti-logarithm of the quantity of say sub t. Sometimes, the coefficients of skew c sub s is adjusted to account for the size of the sample size using the following relation proposed by Hazen in 1930. Skew c sub s is equal to c sub s times the quantity of 1 plus 8.5 over n. From the previous equation, c sub s is equal to the adjusted coefficient of skew. However, the standard procedure for use of Log-Pearson type 3 distribution adopted by US Water Resources Council does not include this adjustment for skew. When the skew is 0, in example c sub s is equal to 0, the Log-Pearson type 3 distribution reduces the log normal distribution. The log normal distribution plots as a straight line or logarithmic probability paper.